Alright, so earlier we saw how we can solve differential equations, and basically the differential equation is kind of a step up where we're looking at how a function changes with a certain variable, and what we have to try and find out is what the integral of that is, or if we integrate that function, what function satisfies that differential equation. So one of the applications that it's easy to see is that the Schrödinger equation itself is actually a differential equation. And so if we look at the Schrödinger equation, we've got an operator, the Hamiltonian operating on the wave function is equal to the energy times the wave function again. And we showed that these here can be considered the eigenfunctions, and this here is the eigenvalue. Alright, so basically you can actually view this as a differential equation. So let's write this out in full. If we write this out in full, what we see is that, let's do this in one dimension, just to make it a little bit easier for ourselves. So the Hamiltonian in one dimension is going to be negative h bar squared over 2m partial derivative with respect to x, and that's times, and so you can see that this is our Hamiltonian. It operates on our wave function, and we're going to get out some energy and the wave function again. And what we're trying to find is we're trying to find a wave function for which this equation holds. And this is how we've solved these differential equations in the past. So it's just that, a little bit more complex, but a differential equation. And often what we'll have to do is make approximations, but in this case, this differential here can be solved exactly for a few really nice simple cases. So you can see here we've got how the function changes. Well, actually, it's the change in the change of the wave function along the x direction. And this operator here, if we operate on certain functions, will give us back just a single value, just a single energy value, and the wave function again. And so a very simple case of that is what's called, where we can actually solve this exactly, is a particle in a box. So what we're going to look at firstly is what a possible solution to the Schrödinger equation is in space. And then what we're going to apply is what's called the boundary conditions, and that is what sets up our situation. And often the most complicated part of solving these differential equations is actually working out the boundary conditions and what those parameters actually mean. Okay, so let's think of a function that if we take the second derivative with respect to a parameter, will give us back the same function. So I'm just going to choose this because I know it works, and you'll always find that in differential equations, and it's not always obvious where we get these from, but generally you can kind of think about sine waves, kind of, or potentially exponential functions being another way of another function that might be able to be solved in this way. But let's just think of a sine wave here. Now, last week we saw that we can take the derivative of this, and I'm going to represent that by just a dash. If we take the derivative of sine, we're going to get cos. We're going to get cos of ax plus b, and then we have to take the derivative of what's inside here, and this is basically applying a substitution rule. And so what we're going to get out is we're going to get out a out the front here. And if we take the second derivative with respect to x, we're going to be left with the cos is going to go to negative sine. We're going to get another factor of a out the front, so we're going to end up with a negative from the sine, and a squared sine of ax plus b. And what you'll notice here is that the only difference between the wave function and the second derivative of the wave function is this factor out the front, negative a squared. And so this is one function that we know that if we take the second derivative, which we saw earlier for the Schrodinger equation, is a pretty good. We want to take the second derivative and we want to get out a number over here. So we've shown that the sine wave is one of those functions that we can solve this for. All right, so let's just put in these two functions into our Schrodinger equation. So the Schrodinger equation that we've got, h psi is equal to e psi, and the Hamiltonian in this case is h bar squared over 2m, and the partial derivative, second partial derivative with respect to x of our wave function. And that can be this here is basically the same as the second derivative, and I can represent it like that. Squared over 2m is going to be equal to e psi. So we basically put this in down here, and we put this into this position. So this is really quite simple. So we've got h bar squared over 2m, and we put this in here, this one here, and we've got negative a squared sine of ax plus b, and on the other side we've got e times psi, which is our function, which is just here, and that is going to be sine of ax plus b. And we can see that the sine ax plus b cancels. So if you divide both sides by sine of ax plus b, they're going to both be 1. And so what we're left with is that a negative h bar squared over 2m minus a squared, and remember this is times these two functions here, is equal to e. And so let's just rearrange that a bit. A squared, h bar squared, the negatives go to a positive because a negative times a negative is a positive. 2m is equal to e. And so now we've actually found out what our eigenvalue is. Our eigenvalue is a squared, h bar squared over 2 times the mass of the electron in this case. So this is very useful. But we want to now find out what our A and B are. So what are A and B? And so this is the step where we have to define what our potential looks like. And this is when we define what's called our boundary conditions. And these are very, very important to solving this problem. So our boundary conditions for a particle in a box, the potential can be considered to be basically a region where there is no potential. So let's say that this is x, and we'll put over here the potential here. So outside of this region here, and that region there, the particle cannot be in this region. It would need infinite amounts of energy in order to get into this region here. And inside of here there's no potential, so this is 0. So the particle can exist in here, in this area here, but it cannot go outside of the boundaries. And we call this length here L. So basically you've got a well that is a width L across. And so because the wave function, or the particle in here, cannot exist outside of this potential, then we say that when x is equal to 0, which is at this point here, I'll just use a different colour, that point there, when x is equal to 0, then the wave function has also got to be equal to 0, because we can't have any density outside of our allowed range here. And so we say that our function, which is equal to sine of ax plus b, when looked at a position 0, has got to be equal to 0. So that means that we've got sine of a times 0 plus b has got to be equal to 0. Alright, so the a goes away in this case, and we've got that sine of b has got to be equal to 0. And so we've got to think about solutions for which this is the case. And we know that a sine wave repeats itself every 2 pi radians. So this is 2 pi. But it goes through 0 every pi radians. And so this is satisfied if we have a multiple of pi. So this would be 1 pi, 1 times pi. We could also have 2 times pi. We could also have 3 times pi. And at all of these places, we are going to have 0 value for our function. And so the condition is that that sign has got to, that b has got to be an integer, which we call n. An integer is just the counting numbers, times pi. And so n can be equal to 1, 2, 3, 4, and so on. And this is the condition for what b is. So b has got to be equal to some integer multiple of the parameter pi, and that's just found out through a simple knowledge of what a sine function is. And the second condition we've got is that when x is equal to L, then the function also has to be equal to 0. And we can see that from here, this picture over here, that when the x value is equal to L over here, then it cannot exist in this area. So the wave function cannot exist in here because it would need infinite energy to exist out in this region. And so we say that when the function at the value L has also got to be equal to 0. And so we put in our function here a times L, because that's the place at which we're evaluating this, plus b. Okay, and this whole thing has got to be equal to this has got to be equal to 0. All right. And we found earlier that b has got to be equal to n pi according to the first boundary condition, and so we can write this again as a times L plus n pi. So basically what we need again is we need a multiple of pi, and so we've already got a multiple of pi here. But what we need is that the a times L has also got to be equal to a multiple of pi, and we can see that. So say if I've got an n value here of 3, okay, so that means that I am at this point here, so 3 pi. Now I need to have a times L to be equal to some integer of pi, so maybe 1 pi or maybe 2 pi, in order for the value of the function to go back to 0. So that's also very important. So AL has also got to be equal to an integer of pi, and we say that k in this case is our integer. So k can take on numbers 1, 2, 3, 4. So you can see that say n is equal to 1, n is equal to 1, and if k is equal to 2, then we're going to get to this point here from our n pi, which is going to be 1 times pi, and then we have to add to that 2 times pi, which is going to be our k pi, and so that's going to get us, this is going to be our 1 pi, and then you're going to go 2 pi, and we're going to end up again at 0. And so this is what determines why our parameters must be integer multiples of pi. Remember, we're dealing with radians, and that's why it's so important that everything has to be an integer of pi. And so now we know that AL has got to be equal to k pi, some number, and we know also that B has got to be equal to some integer times pi. And now we can put that into our first equation that we calculated for the energy, which is going to be A squared times h bar squared over 2m. Because now we know what A is, we can rearrange that A is equal to k pi over L. So now we know what A is, we can put A into here and we can calculate what the energy is. So we're going to have A squared, so that's k pi over L, and that's squared, A is squared in this case, h bar over 2m. So that's going to equal k squared, pi squared, h bar squared over L squared, times 2m. Now, something else that we usually do when we show this answer, which is not always completely clear, but we also have to remember that h bar is equal to h, which is Planck's constant, divided by 2 pi. So if we replace h bar with h over 2 pi, then we get our final answer. So we get that the energy is equal to k squared pi squared h bar squared, and so we're going to replace h bar squared with h over 2 pi all squared divided by L squared to m. So you can see here that I've just replaced this value here with this here. So that's pretty easy. And what we're left with is h squared, and then we're going to have a 4 down here, and we're going to have a pi squared. So we're going to be left with a k squared. The pi squareds are going to cancel, but I'll just do it all in full so you can see. Divided by L squared times 2 times m times 4, because 2 to the power of 2 is going to be 4, and then we got the pi squared. And the reason we did this was to remove this pi squared, so that we have the least number of variables in our last result, and so we're left with k squared h squared over 8, because we got 2 times 4, m L squared. And this here is the solution of the energy for a particle in a box, which is really great. So what we've found here is the energy that it can take. And what we want to find next is the eigenfunctions. So what do the functions look like that describe these different energy values? Okay, so I'll show you that next.